Hey, welcome to this video on Gaussian elimination. Gaussian elimination is a key application of matrices that allows us to solve simultaneous equations. We can take a system of equations that look like this and convert it into something much simpler of the form of this. And A will be our matrix that categorizes all of the coefficients of this system. X is our vector of unknown variables that we're trying to solve for. And A times X gives us solution B, which we have here on the right hand side, that we're trying to work out what X is such that A times X gives us B. And using this process of Gaussian elimination, we can quite efficiently solve this system of equations. So let's take a look at what this is. If we had our example here, where x1 plus 2x2 minus 3x3 is equal to minus 1, so on and so forth, we can represent this in the form of our augmented matrix, which has on the left hand side just the coefficients, so 1, 2, minus 3, minus 4, 8, 2, 5, minus 8, and on the right hand side our solutions solutions are x. On the right hand side is what these are exactly equal to, minus 1, 3, minus 5. And it is A with this line through here, B, and together this is our augmented matrix. And the idea is that solving this system via applying a methodology to the augmented matrix is efficient, quick, and easy, and is how we can work out the solutions x1, x2, and x3. So instead of manipulating the algebraic equations, we manipulate the augmented matrix into a form that looks something like this. If I just push it up here. This here is what we call the reduced form. And the idea is that if it is in this form, you now know that x3 is equal to z on g. And then that gives us what x3 is. So you can plug that into this equation and then you can work out what x2 is. And then you can plug x2 and x3 into this equation and work out what A is. And working backwards here, you'll have your solutions x1, x2, x3. And the zeros are important because they eliminate a variable from your equation here. This is a form of elimination in simultaneous equations as opposed to substitution alone. You eliminate the variables here to get your solution of 1. You substitute it back and use the process that way. It's really important when dealing with matrices here that we record very carefully what we're actually doing to the matrix. So to get it into this form, we apply elementary row operations and then we record it next to the changes to what's going on here. So what can you do? What's fair game? I'll first tell you what they are technically, and then I'll show you an example to try and contextualize what's going on here. With an augmented matrix, you can manipulate it and keep intact the integrity of the system by doing any of the following adjustments to the augmented matrix. Number 1, you can interchange rows with each other. There's nothing special about this being written second as opposed to third, so we could just swap it so that this equation is second on the list. Right, number 2, we can replace a row with alpha times the row. So here, if the right hand side is equal to 3 in the middle, and left hand side is equal to this, we could double the whole thing and have this times 2 is equal to 6. And again, that's not going to change the integrity of that equation. And then lastly, we can replace rows with the addition and subtraction of another row and also multiply and scale that by alpha as well. So it's like if you look at row 1 here, if I added this row 1 to row 2, then I'm adding minus 1 here to the right hand side, and then I'm adding all of these variables to the left hand side. And that is effectively how we try and eliminate a variable to get it into this reduced form. So we slowly work away at our matrix until we get into the reduced form, and then we have solved it. So our overall process of Gaussian elimination is step 1, establish the augmented matrix A, hardline B, apply elementary row operations to achieve the reduced form, or even simpler if appropriate. Sometimes you can get it simpler than that, but aim roughly for that reduced form. And then step 3, use your simplified matrix to solve the system of equations. Okay, so let's take a look at an example. If we start with this one here, which is indeed the one we're looking at on the other page. The first step, of course, has been done for us, getting the system into its augmented matrix form. And then now we want to work our EROs, our elementary row operations, onto this augmented matrix to solve it. So what should we do first? Well, let's eliminate the left column, row 2 and row 3 here. Get them into zeros so that we can remove x1 from the equation, quite literally. And to do that, we can add 3 of row 1 to the second row and subtract 2 of row 1 to the third row. And that will get plus 3 to eliminate that to 0 and minus 2 to eliminate that to 0. So we get that here. And then, of course, we need to follow through the effect that has on everything else. But the reason why we did that was to try and make it simpler and get zeros here for row 2 and row 3. And remember, our ultimate goal is to get it simple as possible, and we're aiming for this reduced form here. So next on our agenda will be to get that into a 0. So how should we do that? Well, there's many ways to skin a cat, but what we'll do here is we'll swap row 2 with row 3, and then we'll subtract 2 of the old row 3 from it. So now we've got 1 minus 2 minus 3, which is our old row 3 swapped with row 2. And then row 3 has become the second row 2 minus 2 row 3. So this is our way of writing down what it is that we're doing. Okay, now we have it in reduced form. We can work out what the variables are. So this tells us that 3x3 is equal to 6. So clearly x3 is equal to 2. Plugging that into the next equation allows us to know that x2 minus 4 is equal to minus 3. So clearly x2 is equal to 1. And then the top equation now tells us that x1 is equal to 3. And so our final solution for this is going to be given here on the right, where x1 is equal to 3, x2 is equal to 1, and x3 is equal to 2. All right, so that's an example here of Gaussian elimination in quite a simple context. Sometimes things can be more complicated though, and the reason for that is that this matrix A here has a particular solution, which is what we just found, but sometimes your approach to solving the augmented matrix will land you not with the reduced form, but with something else instead. And what could happen is that you have an inconsistent system. So not every system of equations has a solution. And if you look at this one as an example here, then as we go and head towards the reduced form, we're going to find a problem with it. So first we can convert all of these coefficients into the matrix here. And then we can work our way down. And for the purpose of illustration, what you'll end up finding here is that when you get to the bottom here, you end up having 0, 0, 0 on the left and then 1 on the right. And that means that 0 is equal to 1, and clearly that's impossible. So this system is inconsistent, which means that the equation has no solution. So inconsistent systems, those are systems that do not have a solution, and they identified in the process of Gaussian elimination when you have zeros on the left-hand side and then still a constant on the right. If this was a 0, that would be fine because you have 0 equal to 0, that's okay. But the fact that this is not constant on the right means that there is a problem. All right, what else could happen? So like I mentioned here, you could have zeros on the left and a 0 on the right, and this will have a different type of solution. So let's take a step back. With 3 equations and 3 unknowns, we are geometrically looking for the intersection of 3 planes. This usually has one solution, But in some cases, it can have infinite solutions which lie on a line of intersection between the planes. And in cases like this, when you're working on getting that reduced form from your augmented matrix, you end up having a row completely equal to 0, which contains no information. And then that means to solve the rows above, you need to let one of the variables equal some free variable alpha. So let x2 equal alpha, and then work out how x3 and x1 relate to x2. And then you get this line, this equation of solutions that is infinite in its possibilities. So let's look at an example of that. Solving this one here with our 3 equations but only 2 unknowns. We have x2 minus x3 is equal to minus 1. That's from this row here. So x3 is equal to x2 plus 1. And then from the top row, we can plug in what we just found about x3 to give us this. Rearrange it, and we get x1 equal to 7 minus x2. And then we also have, of course, x2 is equal to itself, obviously. And now all of the variables are written in terms of x2. So if x2 is just, say, free variable alpha, then we have a solution, or in this case a, sorry, not alpha. We have a solution that looks like this. And this is a line with slope minus 1, 1, 1 and fixed point 7, 0, 1. And any x2 of this form will be a solution to the system above. And of course, there's infinite amounts of solutions because a could be any real number. And that is giving us, in terms of the intuition, this line of solutions that are all valid solutions to the system. Okay. One more thing I want to look at in this video, which is an application of Gaussian elimination and an abstract concept. First of all, what it's called that I want to look at is the null space. And the null space is an analysis on a matrix A, which is the set of all vectors that have A times X equal to 0. So we're particularly looking at this, and we're wanting to know every possible vector X that when you multiply A with X, you get 0. And this set of vectors that achieve this is equal to the null space of A. And we define that and talk about it in terms of mass in our symbols with ns of A. So the null space of A is equal to set of vectors X that achieve this. Okay, and the linear system of A, x equal to 0 is the homogeneous system, and then the linear system AX equal to B is the inhomogeneous system when B is not 0. So interestingly, what we're actually doing is we're separating, let's see if I can block it out a bit better. We're separating AX equal to B as a equation into AX equal to 0, and then having this extra thing on the right, which is this B. And the idea is that there's a relationship between the null space of A and our inhomogeneous system here. But we'll talk about that in a second. Let's first look at an example of determining the null space of A. So if A is equal to this and we want to work out the null space, we need to establish a augmented matrix with the zeros on the right. And then we just solve for the solutions to this. And what we end up getting here is 0, 0, 0 equal to 0 on the bottom. And now we have the opportunity to work backwards to work out the solution here. And if I'll leave this, you can pause if you like and solve this yourself mathematically. But what you end up getting is x2 equal to x3 and x1 equal to minus x3. So because these two are in terms of x3, then we can think of it like this, where x3 is equal to x3. And now we know how to represent all of them in terms of x3. So it's minus 1, 1, and 1. so vectors of this form here, will always satisfy this relationship. Because clearly x3 times 1 is itself, x3 times 1 is itself, x3 times minus 1 is minus itself, and that is following this relationship here. So this is our null space. It's a set of vectors that have this form. Yes, that's how you solve the null space, is if you work through the augmented matrix with zeros on the right. Okay, so connection between the inhomogeneous and homogeneous systems. If AX is equal to B and P is a fixed solution, then the complete set of solutions is X equal to P plus Y, where Y is an element of the null space. So P being a fixed solution, as in just one specific solution to this, plus anything from the null space, will give you all of the possible solutions to this system. So I've kind of rewritten what this really means, because it's a complete set. It means this set is equal to this, and that is equal to this set. And you can look at it with these two if statements here. So if X and P are solutions to AX equal B, then Y equal to X minus P is in the null space. So we can work out the null space by taking the difference of any two solutions. And then if Y is in the null space and P is a fixed solution to AX equal B, then P plus Y is also a solution. Okay, this is fairly easy to prove. You can imagine it as, well, why don't we actually look at one right now? Just grab some paper. 1 second as I grab the paper. Okay, so if we look at up here, if we look at these two statements below to really get an understanding of what's going on here, if X and P are solutions to AX equal B, then Y, which is equal to the difference of them, must be in the null space. So consider Y, which is equal to X minus P, where AX is equal to B and AP is equal to B. So they're both solutions, which means they both, when multiplied by A, equal to B. So if Y is equal to this, we can investigate what happens when we multiply A by Y. And according to this, Y is in the null space. So we're investigating, does this equal to 0? Because if this equals to 0, Y is in the null space, and that's what this theorem is claiming. So AY is equal to A multiplied by X minus P. And that's because that's what Y is. And expanding this out, we get AX minus AP. And then those are both equal to B. So we get 0. So therefore Y is in the null space of A. Simple. And then on the flip side, we can consider what will happen when we look at P plus Y. So consider X equal to P plus Y, where P is a particular solution and Y is in the null space. And what we want to show is that X is also a solution. So A multiplied by X is equal to A multiplied by P plus Y, which is equal to A multiplied by P plus A multiplied by Y, which is equal to B plus 0, which is equal to B. And so that is what will make X also a solution. Therefore, X is also a solution. Okay, so very simple proofs. And what this is showing is that this theorem is indeed accurate, that if AX is equal to B and P is a fixed solution, then the complete set of solutions is just adding from our particular solution anything from the null space. That will give us another solution. And then also working backwards from here, we know it's the complete set, because if we look at the difference between any two solutions, X minus P, then we will always generate something from this null space here. And that's how we know it's a complete set. All right, that's everything in this video. So thanks for watching, and I hope you learned a lot about Gaussian elimination and then also null spaces. Thank you.